the negative sign is from the cosine 180, just like before. And let's say the mu k is still 0.3, so I can write that this is negative mu k times Fn times S. Okay? What is Fn? And again, this is now a chapter 4 or chapter 5 problem. You must have done multiple times, but right, normal is not mg in this case, right? So how do you get the normal? Again, draw the free body diagram. I remember what it is. So it's mg cosine theta, mg cosine 30, but if you draw the free body diagram, it's going to be straightforward. So let me do that, although at this stage you should have already known how to do the free body diagram and solve for Fn. So that's Fn there, that's mg there, and the displacement. So the free body diagram, you can consider this to be the y-axis and this to be the x-axis. Okay, so that's y-axis right there, like this, and x-axis. And the angle right here is going to be theta. Okay, whatever angle theta you had here. Remember, if this is theta, this is 90 minus theta, right? That if this is 30, that would be 60. If that is 60, this should be 30, because they're also perpendicular to each other. So I only focus on this theta. So you don't need to write 60 degrees anymore. So you can just write 30 degrees. So all you have to do is that tilt your head, because the axis is now tilted. Because y is there, x is there, so just tilt your head, or just rotate the paper. Now you have the normal axis. Right? Rotating is easier. When I do this on the computer, it's not easy to rotate, but now it is. So now all you have to do is just write all the y components and set that equal to 0, and that's all I'm going to do. Okay. So sum of Fy equal to 0, so that means Fn is y, and mg cosine theta, right? Minus mg cosine theta is y, and that's the only y forces. Fk is purely in x-axis, so it has no y component. So only two forces have y component. One is the normal, and the other is mg. Mg is not along y, so you have to get the component. So when you get the component, that would be the adjacent component, and that's why you have cosine of that angle. Mg cosine 30 would be there. Okay. So Fn is mg cosine theta. I told you. Okay. So easiest thing to remember: if no other force is being applied, if the object is resting on a plane surface horizontally, then it's mg. The normal is just the weight, like someone suggested before. If the surface is tilted, then it is mg times the cosine of tilt angle. So that's how I remember. And if there is no other force, then that's what it is. If someone is actually applying additional force, then you will have to consider that additional force in the free body diagram, and that would also contribute to the y, and then you have to include that also, like we did in the previous problem, right? So I think we are pretty close to the answer. So the minus mu k, I consider 0.3 in this case. Fn is going to be mg cosine 30 degrees times the displacement, which is 2 meters, and that's what your answer would be. Right? So any problem you see in chapter 6 now, you should be able to solve. Okay? One more thing that I want to point out in this chapter is that there is one section that deals with work energy theorem that allows you to calculate the velocity. Okay? So I'm gonna do this in this problem. Okay? So the total work done, W total, is going to be work done by gravity plus work done by normal plus work done by friction. right? That's the total work, because these are the forces that are being applied on the object in this problem. So, work done by gravity is positive, and that's 19.6 joule, plus 0 minus work done by friction is always negative, minus cosine. Can you give me this number, please? 19.6 times, how much? 10.2 joule. Okay. Equal to, again, 9.6. Oh no, 9.41 joule, and it's positive. Okay, so that's 9.4. So we are able to calculate the total work. The good thing about, yes.
Why is it minus 10.2?
Why? Oh, this is the work done by friction, right here. And someone calculated, I didn't calculate. Someone calculated, okay? If you get a different number, let me know. Okay? Yes.
Yeah, I have a question. Doesn't the gravity also have a component with the direction of the surface? Direction of the 2 meters?
Yes.
Don't we have to do that?
If you're trying to calculate the normal, you don't need the x component. The normal is only y.
No, I mean for the total, because gravity is also moving the object in that direction.
Yes, we calculated right here. So,
Oh yeah, that's happening.
okay. You don't really need to, right. So either this or this.
So both are the same.
Both are the same.
And I only have to use one.
You only have to use one.
Oh, okay, so I.
You only have to use one. Work done by gravity is just one, okay? No, not in different components. Okay.
You got negative at friction S, or like for the, and then you like subtracted it, so it was kind of like you just added the.
No, the negative sign is only in one place, okay? I added it. To get the total work, I have to add, so WG plus WN plus WF. Okay, I added, but the WF itself is negative.
Yeah, okay.
So,
Right.
makes sense, right?
Yeah.
Thank you for helping me. Turn up? Oh. Thank you so much. Okay, how much time do I have? 20 minutes? 25, okay. So now, the good thing about the total work, so work total, work energy theorem, you already did this, so it comes from chapter 2. When you wrote this equation, b squared minus b0 x squared equal to 2ax times x minus x0. Remember that equation? That's from chapter 2, right? So if you consider this x minus x0 as s, which is what we have been saying here in this chapter, right, displacement, and let's say b2 squared minus b1 squared equal to 2a times s, right? If you multiply this with, or you can write 2as equal to b2 squared minus b1 squared. If you multiply by m, you get ma s equal to b2 squared minus b1 squared divided by 2, and ma is force times displacement. So if it is a parallel component of the force, then you basically get 1/2 m, because you need to multiply that m. So you get m b2 squared minus 1/2 m b1 squared. So that's what you did, okay? Very quickly, going back to how this work energy theorem was derived. You don't need to know how to derive this, I think, but you just need to know how to use it. So we call this as K2, and we call this as K1. So it's K2 minus K1. K is called the kinetic energy, and that's the final kinetic energy, KE final, and this is KE initial. Okay, so we had total work done, and now we can calculate this, or total is 1/2 mv2 squared minus 1/2 mv1 squared. Okay, now in this problem, I said this object is sliding down. Let's say it starts at rest. So starts at rest and travels 2 meters there. Now we can calculate what the velocity of that object is when it reaches that 2 meter distance. Okay, so just think of a realistic situation, right? You're let's say you're trying to deliver a big package. It could be a fridge, for example, right? And they put a inclined a plank, and then they just slide the object downward. So now that it is being acted on by the gravity, the object is going to slide and will gain speed. So what will be the velocity of that object when it reaches that 2 meter distance? So that's what we want to calculate. So what will be the velocity? Can you calculate this? Let's say the velocity here is v1, which is 0, because it starts from rest, and we just need to calculate v2. What is the final velocity there? Now, the nice thing is that we already know what the total work done is by all the forces, by gravity, by friction. There was no other force, by the way. So the total work was 9.41 joule, equal to the initial velocity is 0, so we don't even need that. So I have just 1/2 mv2 squared, and look how simple it is to calculate the velocity. Okay? You could have, of course, calculated the velocity using chapter 5, in which case you would have to solve the free body diagram. Then you would need to write the x equation also. So you would write y equation and x equation that have the acceleration. First calculate the acceleration, use that acceleration in the distance, and then the same equation, this one, and you would be able to calculate the velocity. But once you know what the total work is, then you can just use that and calculate the velocity. So 1/2 m is 2 kilograms v2 squared. So basically, or if you just write v2 is square root of 2 times total divided by m, and so 2 times 9.41 joule divided by m, which is 2 kilograms. So that would be your velocity. Is that okay? So can you calculate the velocities of these in these kind of problems? Okay.
Can I ask one more question?
Sure.
Why the gravity in both directions is the same? Is that because the sine of one angle is always the cosine of the other one? Because if I have 30
Yes.
so
Yeah,
no matter
because-
how the angles are, they add
Yes.
up to 90.
Mhm.
So sine equals.
In one case, you're calculating the component of force along the horizontal, along the incline, and the other case, you're calculating the component of S along the vertical, and it's the same. Okay, so it's like you're writing something like F cosine theta times S, or you're doing F times S cosine theta. So in this case, you're calculating the component. Okay, so it's almost like that. So let me ask you a very simple question. This is what I ask most of the times. If you know, if you go to a tall building, right, and you drop an object, and if you can time it, how much time it takes, you should be able to calculate the height of the building, and also how much velocity the object is going to be at the end of the trajectory, right, end of the or the flow, right? How do you calculate that? Just go to library, right, and then you drop an orange, okay, and it takes let's say 2.3 seconds. What is the height of the library? Yeah, you can use chapter 2. Okay. Do you know the time? So you would use this equation, right? You would use y minus y0 equal to v0 yt minus 1/2 gt squared. And because you just release it from rest, you don't need this term. So pretty much it's 1/2 gt squared. That's how you calculate the height. If you know the height and also the time, you can calculate the gravity. You go to Mars or other planet, unknown planet, someone asks you to calculate what is the acceleration of the gravity in that planet, then you would just take an orange with you. Or it could be anything, right? And then time it, how much time it takes to drop through that height, and use that height and get the gravity. So it's really simple, right? So, but now I'm going to ask exactly the same question, but use the work energy theorem to calculate the velocity. Okay. Once you get the height, you can also calculate the velocity by using this. Vy equal to v0y minus gt. So v0y is 0 if you just drop. So g times t is going to give you vy. So it's easy if you know the time, how much time it takes to fall, or if you know the height. In this problem, I'm going to give you the height, and you calculate the velocity. Okay, so that's what the question is. Question: you drop something from a certain height, and this height, let's say, I don't know, 15 meters. Okay, 15 meters is not that high, and it is dropped, and it goes there. Okay, did you have the first exam already? So probably that could have been a problem in chapter 2, right? So you go to the tall building, drop it, and you know the height, how much time it takes, what is the velocity, right? At least that's the minimum concept, minimum understanding you should have after you graduate or pass this course, right? That's what the expectation is. So in this one, if you use chapter 2, I would just use the third equation, vy squared minus v0y squared equal to negative 2g y minus y0, right? I have the height right there. I have the initial velocity, which is 0, because I said drop it from rest. So what do I have? I have vy is basically square root of 2g times h. Remember, this y minus y0 is negative 15, because you start from here, end up there. So y minus y0 is negative, so this negative and negative will cancel, and you get 2gh positive. So that would be your velocity. Let's try work energy theorem to get the same expression or same answer, whether it works or not. So I'm going to calculate the total work. So work energy theorem just means that total work is equal to K2 minus K1, right? That's all it is. So work done by all the forces. How many forces you have there? Just one, and air resistance. We ignore air resistance in chapter 2, so we ignore here as well. Okay. So let's ignore the air resistance, and we only have one force. What is the work done by gravity in this case? So Wg is equal to force of gravity, which is mg, right? Mg times the displacement. What is the displacement here? 15 meters. Or let me write h. Is that okay? And is it positive or negative? Work done by gravity. Positive. Why? Same direction. Force is downward, and your displacement is also downward. Positive. Force is downward, displacement upward. If you pick up a book, right, the work done by gravity is negative because gravity applies downward force, but the displacement is upward. The work done by you is positive because you apply the force in the upward direction, and the displacement was also in the upward direction, so work done by you is positive. It's that simple. Same direction, positive, opposite direction, negative, because that 180 degrees. So that's mgh. So that's the total work. What I can do is that total work is equal to K2 minus K1, which is 1/2 mv2 squared minus 1/2 mv1 squared. I told you that initially it is at rest, So I have the same equation that I used before, right here. Okay, so I'm gonna write, so mg times h is equal to 1/2 mv2 squared, so this m cancels out. So v2 is square root of 2gh. Does that match with this? So it's the same thing. So we actually started this work analysis theorem from here. Okay, so no wonder it gives you the same result. Okay, so you don't need to know the mass. If you know the mass, you can multiply and calculate, but it's really simple. Okay. The good thing about this work energy theorem is that you can also include the air resistance in this. Okay. If the work done by friction or the air resistance is such and such, then you can include there in the total work, and you now get the new velocity. From chapter 2, it's difficult. In chapter 2, there is no concept of friction, right? Maybe it is reflected by the acceleration. Maybe it's not exactly 9.8. Maybe the acceleration is now 8.2 because of the resistance. You can say something like that, but here you can calculate the work done by friction, calculate the work done by gravity, and add them together and set them equal to K2 minus K1, and you can calculate the new velocity.
It's still kind of confusing to me why you don't need to know the weight of something.
You don't need to, okay, because the mass is going to cancel out. See, mass cancels out, but you will most likely you'll be given, a mass, 2 kilograms or 5 kilograms, which is mg, which gives you mg. If it is not given, just keep as m. Okay, and it's going to cancel out with if nothing is given. Okay, just keep m. But it is weight though. Mg times the height is the work done by gravity. That's what I did. Force of gravity times the displacement. Right? So that's the weight. Any question? I think I sampled all the types of problems that you have in the book. So you should be good. Okay. You still need to do a lot of problems though. That's great. You got it. Yes. Work done by gravity plus the work done by friction. You add them together. That's all. So all you have to do is write total work there.
Oh.
Okay, so only one additional concept that you need in chapter 6, which is called power. Okay, so power. I'm not going to do anything with this because the problems are very simple. You can do them yourself. There's not much. But what is power? I want you to understand what power is, and that's all. So not more. What is power? Yes, it is. So in everyday life, power is different, right? You can have power. You have political power or administrative power or something like that, right? But that's not what it is in physics. Power is P average is defined as how fast you can do the work. It's delta W divided by del T. So how much work you can do in a certain amount of time. If you can do the same amount of work twice as fast, then you have double the power, right? So that's how it is defined. So it's actually kind of counterintuitive. If you think about the political power, Congress has a lot of power, but they're the slowest to work. So it's just the opposite, okay? So nothing gets done, and yet they have the most power. In physics, it's just the opposite, okay? Yes. This is chapter 6. Still chapter 6. But always remember that faster you do the same amount of work, more power you're going to have. So really simple. The same thing could be written slightly differently. If you write this delta W as force times displacement, delta S, divided by delta T, then you can write this as FV, force times the velocity. Sometimes you'll be given the velocity and the force, you can still calculate the power, because this delta S over T is velocity. And actually these are vector quantities, so the actual answer is gonna be F dot V, okay? So, if you're given the force and the velocity, you should just calculate the power of something. So there is not much. So the problem would be like, a force is pulling a box with, a box by, it pulls by 2 meters and the force is 10 Newton, and in 5 seconds, what is the power? So you just calculate the work done just like what you did before, and then divide that by the time, 5 seconds, and you get the power. That's simple. So nothing more difficult. So this finishes chapter 6. Let me know if you have any questions, because I think we sampled pretty much everything. Yes.
I can see the notes up there.
Cool.
What's that called?
I'm gonna start chapter 7, if
Yeah.
I have time. 10 minutes? 5? Is that- 5 minutes, okay, in 5 minutes I can start. Don't worry, yes. Excuse me. Oh, okay. Sign in sheet, please sign in, okay?
Where's the sign-in sheet?
Nobody is interested in staying.
What is it?
So chapter 7 is pretty much continuation of chapter 6, and the problems will be much easier in chapter 7. Much easier, okay? So the concept is that you're gonna have to write the work done by gravity as difference in two quantities. So if you have, let's say, something falling from y1 to y2, and then you want to write this as work done, so work done by gravity, you can write this as mg y1 minus mg y2. These are coordinates, okay? Y1 could be 10 meters and y2 could be 0, right? So let's say y1 is 10 meters and y2 is 0 because it's falling. So 0 minus 10 gives you minus 10, and work done by gravity has to be positive. So this is bigger number, this is smaller number, and that's why this is how you have to write y1 minus y2, not y2 minus y1, to keep it positive, okay? And we call this u1 minus u2. So u is just mg times y. mgy, if you put 1 there, it's u1. You put 2, it's u2. So what is u? It's called potential energy. It's called gravitational potential energy. So potential energy is defined as the potential to do work. Okay, if you have the potential to do work, you have potential energy. So for example, the water stored in a dam, and then you release the water through a pipe, and then it has potential to do work. If the water is in the lake, it has no potential to do any work. If it is on a dam higher up and you release it, it has the potential to do work. So in the form of mgh, you have certain height and you can get that energy. And that's called the potential energy. So if I write this equation, so you have, right now the total work, W total, is equal to U1 minus U2 in this case, because only the gravity does the work, so that's the total work also. But in chapter 6, you also wrote W total equal to K2 minus K1. So what does that mean? They are the same. So you can write U1 minus U2 equal to K2 minus K1, and that also means that K1 plus U1 equal to K2 plus U2. So this means that if you add the kinetic energy with the potential energy, it is conserved. It's the same in one place versus the other place, okay? So it's the same. I know you're anxious to get out. Give me 2 more minutes and I'll be done, okay? 2 more minutes. Is it clear that, go back? Yes. I'm gonna read back. Okay. So, so I can write K1 plus U1 equal to K2 plus U2. So this means that the sum of kinetic and potential energy is equal to sum of kinetic and potential energy at any other point. So I'm gonna solve one problem and you will see how easy it is to do the problems in chapter 7. Just one example and that's it, okay? So let's suppose we have a pulley, and this is from chapter 7. You will see that there is a problem just like this. Okay? And let's say this is, I don't know, 15 kilograms, and this is 6 kilograms. Okay, so this is M1 and this is M2. And they are tied with a string, string that passes over a pulley. The pulley is frictionless and very light. And the problem will ask, if you release the system from rest, obviously the 15 kilograms object is going to hit the floor, and you want to calculate what is the velocity of both masses. Velocity when M1 hits the floor. How do you calculate this? Do you already know how to calculate this? You can use chapter 5. I think you did similar problem. You draw a free body diagram, put the acceleration. Once you get the acceleration, you can calculate now the velocity, right? But here, it's much simpler. You don't need to draw a free body diagram, nothing. All you have to do is write this equation. So K1, U1 is just when you release, and K2, U2 when it hits the floor. So 2 different points. So I'm gonna do that. So K1 plus U1 equal to K2 plus U2. So K1, what is K1? What is K? Kinetic energy, right? 1/2 mv squared. So what is the velocity of these objects just when you release? 0. So that's not even there. See? What is U1? U1 is the potential energy. Let's suppose the potential energy is 0 at the floor, and any height you have will have mgy. Mgy is the potential energy. So which one has potential energy, which one does not? The 15 kilograms has potential energy because it has potential to do work. It has potential to fall. Okay, so that one would be M1 Gy. Y here is 2 meters. Equal to K2. K2 now means that when this object hits the floor, that's when the kinetic energy we're talking about. Okay, so that means it is 1/2 mv squared plus 1/2 m2 v squared, because the second mass will also be moving with the same velocity. It will be going up, but it will be moving, right? I can draw the second diagram here, maybe. So this will go up by 2 meters, and this is going to be M1, this is going to be M2. That's bullied. And I'm sorry, it's already 2 minutes. Yes? So that's the second situation, right? When the first one hits the floor, the other one goes by 2 meters. So then you also need to put this U2, which is M2G times Y. Okay? So V, I'm interested in calculating V, so that would be M1 plus M2 V squared, and I write this M1 minus M2 Gy. So see how quickly I can get the answer. M2 G divided by so that's what you get. Okay, take a picture, and that's all.